You there?
Sparrow here.
Sparrow, this is Tango. You read me okay?
I read you, Tango.
We have a code 6 on Alcatraz. You have your compass on you?
My compass?
Affirmative. We have a target down there under cloud cover.
Roger that.
That target is Gold Viper.
Viper? I thought he died in the avalanche.
Negative, Sparrow. He's on Alcatraz with a hostage.
A hostage?
Sparrow, you got a rifle with a scope?
Negative, Tango. I have an umbrella.
Then make it rain, Sparrow.
Roger that. I'll be right down. Tango, I got no visibility here.
Yeah, your target is going to be at 130 degrees. You got this, Sparrow.
Copy that. Why, hello there. My name is Joey Young, also known as Sparrow. And in this video, we're going to be discussing navigation, advanced concepts. And I did make a previous video called How to Use a Map and Compass in Detail. And I highly recommend that you watch that video first before you take a look at this video, because there's a lot of foundational concepts in that video that explain the parts of the compass and how the compass works and how to take a bearing. And you're going to need to know all that stuff in order to understand some of the stuff that we're going to be discussing in this video. So here, I'm standing on a mountain peak. Specifically, I have Mount Conness in the background here, and the north ridge of Mount Conness running this way. And this is a very special place for me because it has a very special significance. This was the very first true mountain peak that I climbed. And I've chosen this place because what we're going to do is we're going to perform a little bit of an experiment. In the first video, I showed you how to determine a landmark based on a location that you know. In other words, if I know where I am, I want to know what I'm looking at. In this video, I'm going to do a little bit of the opposite. Now I'm going to tell you where landmarks are, but I'm not going to tell you where you are. Now I'm going to show you two landmarks that you know, Mount Conness behind me and North Peak over there. And using those two landmarks, we're going to try and determine where we are on the map. So we were just up there a minute ago, and let's pretend we came down into this valley here. And so we know that Mount Conness is behind me right there, and North Peak is right over there. So knowing these two landmarks, let's pretend that we're lost in this basin. And what we're trying to do is find our location on the map, knowing that that's Mount Conness right there, and that's North Peak over there. The way we're going to do this is we're going to take compass bearings of each landmark, and then where those lines of sight intersect on the map, that will be our position on the map. We're going to do this with two landmarks, Mount Conness and North Peak. But what you're going to find is that when you use 3 or more landmarks, the accuracy of pinpointing where you are on the map is going to increase. However, I'm going to use 2 landmarks in this example because I actually think that 3 landmarks is actually very unrealistic, because the idea is that you don't know where you are. So if you can see 3 landmarks that you can identify, you probably already know where you are just by looking at those landmarks. I also want to explain one other thing, which is the narrower the angle between the landmarks, the less precise your location is going to be. And I'm going to explain why this is when I show you how I plot these bearings on the map, but it kind of makes sense when you think about it logically. For example, if I was to take a bearing of that tower on the right, which I call Tower 1, and Mount Conness in the distance, those 2 points are very close together. And so if you think about it, it's almost kind of like taking a bearing of the same landmark, because they're so close together in terms of the angle. So the wider apart the landmarks are, the more accurate your position on the map is going to be. In order to take bearings of these landmarks, I'm going to be using this base plate compass here, which is a Sunto MC2G. This is the same compass I used in the how to use a map and compass in detail video. And I also have a map here. This is map number 308, Yosemite Northeast. Using this map and this compass, I'm going to take bearings of these 2 landmarks and then plot them on the map. All right, so I have my compass here, and this is the compass I'm going to be using to take bearings of these landmarks. And I want you to see that I actually set my declination before I left to 12 degrees east. And that's because I checked it this morning on www.magnetic-declination.com for the location that I'm standing. And I'm actually going to do one more thing before I take these bearings, which is to remove my watch, which is stainless steel. And I honestly don't think a stainless steel watch is going to make any difference at all in these bearings, but I'm going to go ahead and remove it just to be sure. And so what we have here is North Peak here and Mount Conness over here. And Mount Conness is pretty far away, but North Peak is pretty close. I almost kind of have to crane my neck when I look at it. So when I take my bearings of these 2 landmarks, I want to try and figure out how I want to position my compass so that it's flat and I'm not tilting it like this. You'll also notice that in the previous video, I was able to kind of look through the mirror here because my landmark was kind of right in front of me on the horizon, but now it's up high. And so I think it makes more sense to line the landmark up with the top of the mirror. And looking at North Peak for a moment, it's kind of hard to tell exactly where the summit is. I mean, there's a few spires and stuff, and sometimes it is kind of hard because of all the foreshortening. But I do believe it's that one on the far right. And so I'm going to go ahead and use that one as my basis for my bearing here. And taking my care here to make sure the compass is flat, lining the top of the mirror up with the summit spire, and then rotating the bezel just like before until the needle is boxed. I'm getting 288 degrees for North Peak. And now let's go ahead and do Mount Canas, which is right here. For Mount Canas, I'm going to do the same thing. Hold my compass up like this in front of me, keeping it flat. And I'm lining the top of the mirror up with the summit. Again, with Canas, it's a little hard to tell exactly where the summit is, but I'm gonna do my best and try and figure out where along that ridge the summit is. And then I'm gonna rotate the bezel just like before, so my needle is boxed. And I'm getting 228 degrees for Mount Canas. Okay, so now we have bearings of our two landmarks, North Peak and Mount Canas. And I still have the bearing from Mount Canas in my compass because that was the last landmark I took a bearing of. But as usual, I recorded both bearings into my logbook. And so what we're going to do is we're going to plot those bearings onto the map. Now in the previous video, I had used this kind of complicated system where I taped a tape measure down to my desk. And that was because I had a lot longer distance to plot. But this time, the distance that I have to plot on my map is much shorter. And so instead what I'm going to do is I'm just going to use my base plate on my compass and extend that with the mirror like this and use that to plot these two bearings. Okay, so before we plot our bearings onto the map, I just want to show you something real quick on this particular map. So these black lines here, they point to true north. And these are what are known as true meridian lines on the edge of the map. However, these blue lines here, they point to what is known as grid north. And on this particular map, if you look closely, what you can see is that the blue lines and the black lines are not completely parallel. In fact, the blue lines are slightly to the west of the black lines. And so then, if you recall from the previous video, what we were doing is treating these blue lines as if they were meridian lines by taking our compass, placing it on the map, and then aligning the meridian lines of the compass, which are the red ones, with the blue lines, which I call the meridian lines of the map. But if we were to do that on this particular map, we would actually not be aligning our compass with true north. We would be aligning it with the blue lines, which are slightly to the west of true north, and not true north here. And so what we need to do is figure out what the difference is between the black lines here, which are true north, and the blue lines here, which are slightly to the west of true north. So in order to do that, we have a protractor here. And so what I'm going to do is I'm going to measure that difference by placing the protractor on the bottom of the map like this, and then aligning it so that the middle right here is pointing true north in this direction. And that way I can figure out the difference between true north here and grid north here. And from looking at this map, if I get it aligned nice and precise, it looks like there is an approximate 2-degree difference between true north and grid north. And so what that means is that if I was to take my compass and place it on the map like this, and then rotate the bezel so that the red lines, the meridian lines of the compass, were aligned with the blue lines, the meridian lines of the map, I would actually not be aligning my compass with true north. I would be aligning it with a line that is 2 degrees west of true north. Because really true north is actually not here, it's actually more over here. All right, so let's go ahead and plot these bearings onto the map. The first bearing we took was of North Peak, and that was a bearing of 288 degrees. But if we were to plot this particular bearing onto the map, by lining up the red meridian lines on the compass with the blue meridian lines on the map, we would not be plotting the bearing we took, but a bearing 2 degrees east of it. And that is because true north is here, but we are not lining our compass up with true north when we use these blue lines. We are lining our compass up with a line that is 2 degrees west of that. So in order to compensate for this difference, what we're going to do is, instead of plotting 288 degrees, we are simply going to subtract 2 degrees from that to get 286 degrees. And I'm explaining in a second why we subtract and why we don't add. But for right now, just follow along with my example. So this right here is North Peak, and I'm going to line the base plate up with the summit of North Peak and try and find some blue lines that I can use, perhaps these ones right here, and then rotate the compass, not the bezel, until I can get those lines more or less parallel. And as you recall, I don't like to stack the lines, I like to keep them parallel. That is just so I can see them easier. Let's go ahead and plot that line right there. And that represents the line of sight that we observed in the field. So we are somewhere along this line. Now let's go ahead and plot the line for the second landmark, which was Mount Conness. And that was a bearing of 228 degrees. And for Mount Conness, just like with North Peak, we're simply going to subtract 2 degrees from the bearing we took to get 226 degrees. So Mount Conness is right there. Let's go ahead and line the base plate up with Mount Conness's summit. And we're simply going to rotate the compass, just like before, trying to find some blue lines that we can use, perhaps these ones right here, up with the summit here, and then rotate the compass until those lines are parallel. Again, I don't like to stack them. I like to have them parallel like that. That looks pretty good right there. Let's go ahead and plot that. And it looks like we were right about there when we took our bearings of these two landmarks. Okay, so I want to explain briefly why we subtracted 2 degrees and we didn't add, with a simplified example. So imagine instead of taking 288 degrees and 228 degrees in the field, we took a bearing of 0 degrees, so that'd be true north. If we were to plot that bearing onto this map by lining up the red lines and the blue lines, hopefully you can see that that would not be a line that would go to true north, because of the fact that these lines do not coincide with true north, which is here. It's really that true north is not here, it's here, because of this difference. So in order to compensate for that, I would need to slide my bezel over like this, 2 degrees. And that is exactly what we did when we plotted these bearings. We simply subtracted 2 degrees. So in my how to use a map and compass in detail video, a lot of people asked about the clinometer. And I said in that video, you're probably never going to use this feature of the compass. But because so many people asked about it, I'm going to go ahead and explain to you how this mechanism is going to work. So what the clinometer is there is a black arrow, and that black arrow points down. As I tilt the compass, that black arrow remains pointing down no matter how I tilt it. And so then you can use this mechanism in order to determine the relative height of an object you're looking at. Okay, so what I'm gonna do is I'm gonna set my compass to west, and as a right-handed person, I'm gonna have it this way so that when this black needle falls, it's gonna be on 0 degrees when it's level. And when I turn the compass this way, it's going to measure the number of degrees the angle that I'm turning it. So it really is just falling down with gravity, and as I turn it up like this, the black needle continues to point down because of gravity, and that is measuring the angle. So I'm going to go ahead and measure the angle to that summit, and using that angle, I can figure out, if I know the distance, I can know the height. I can figure out the height. So let's go ahead and take that measurement. And it's a little hard to show on camera, but I'll show a close-up. But I am getting about 17 degrees. Okay, so here's a close-up view of the clinometer. And you can see that it's that black arrow on the bottom there. And it just basically falls down with gravity. And as I tilt the compass, the arrow continues to point down, but it's now pointing to a number of degrees. And so that's measuring the angle that I'm tilting the compass. The angle on its own doesn't have a lot of use, but you can use that angle to compute a height. All right, so here's a look at the map. And this right here is Mount Conness. And this is the place where we were standing. So what we need to do is we need to figure out what the elevation is of this spot right here. And looking at the map, you can see that this bold line here is labeled 10,500 feet. And this bold line here is labeled 10,750 feet. And there are 5 lines between these two, which means each line must be 50 feet. So looking at these lines, if I jump over to this one, 50 feet higher than 10,500 feet, this one must be 10,550 feet. And it is pretty close to the place we were standing. So I'm going to go ahead and say we were at approximately 10,550 feet. All right, so we just took our measurement of the angle between the place where we were standing and the summit of Mount Conness, and that was 17 degrees. So what we need to do now is we need to measure the distance between those 2 points. And so what I have here is the scale located on the back of the map. And so what I have here is a piece of paper, and I'm going to use it to mark off where the 1 mile marker is, the 2 mile marker is, and then while I'm at it, I might as well also do the half mile markers. All right, so here's a look at the map, and this right here is the place where we were standing, and this right here is the summit of Mount Conness. So what I want to do is I want to use this piece of paper that I just marked to measure the distance between these 2 points. I'm going to mark that right there. And so what I need to do now is I need to figure out how far along this second mile is so I can convert this into feet. So if I look at this ruler here, it looks like there is about 4 centimeters or 40 millimeters per mile on this particular scale. And so what I need to do is figure out how far along this second mile we are. And so looking at the ruler, it looks like we are about 11 out of the 40 millimeters. All right, so we determined we were 1 11/40 of a mile from Mount Conness. And so what we need to do is we need to convert that into feet. So 1 mile is equal to 5,280 feet, and 11/40 of a mile is equal to 1,040 452 feet. So if I add these two together, I get 6,732 feet. And that is the distance from Mount Conness. All right, so I've gone ahead and I've drawn the problem on the board here. Let me go ahead and explain to you how we're going to solve this problem. Remember we were in the field and we had our compass and we tilted it and we used the clinometer to measure the angle between where we were standing and the summit of Mount Conness? Well, I want you to picture that this is us and this is the summit of Mount Conness. And we measured this angle here and it was 17 degrees. And we also measured the distance, and that was 6,732 feet. So knowing the angle and the distance, we can figure out the height, which I'm going to call x. And really it's the relative height, because if I take the summit elevation of Mount Conness and I subtract the elevation where we were standing, 10,550 feet, I get x, which is basically this side of this triangle. And so in order to solve for x, we're going to need to use something known as trigonometry. Now you might remember trigonometry from your high school math class, but there are three main trig functions: sine, cosine, and tangent, and formulas that go along with each one. But before we talk about which one of these three functions is appropriate for solving for x, we first have to name the sides of this triangle. So the side that is opposite from the angle that you measure from is called the opposite. The side that is adjacent to the angle that you measure from is called the adjacent. And the remaining side is called the hypotenuse. And although the hypotenuse also touches the angle that you measure from, unlike the adjacent, it does not touch this angle, which is a right angle, or 90 degrees. On a side note, if you know this angle, 17 degrees, and this angle, 90 degrees, you can figure out what this angle is. Write down in the comments if you can figure out what this angle is. But right now, we're solving for x. And so the question is, which one of these three trig functions is appropriate? And so there is a handy mnemonic to remember the formulas for each one of the trig functions. For sine, it is SOH. For cosine, it is CAH. And for tangent, it's TOA. SOHCAHTOA. And so these letters here, SOH, the O, the H, the A, they all stand for the sides of this triangle. O, H, A. And so the question becomes, which one of these three formulas do we want? Well, we know we need an O, so that immediately rules out cosine, because it doesn't have an O. And we also know what A is, so that also rules out sine, because sine does not have an A. So it must be tangent. So we are going to use the tangent function to figure out what x is. So now that we know the angle and the distance, we can use the tangent function to compute the height. So I'm going to write down tan 17, which is the angle, and the formula for the tangent function is opposite over adjacent, and the opposite is x, so what we're trying to solve for, and the adjacent is 6,732. So now we have this equation here, and so what I want to do is I want to get x by itself. So I'm going to multiply both sides by 6,732, like this. So these cancel out, and I'm going to move x on this side. So it's x equals tan 17 times 6,732. And so our graphing calculator has this tan button. So if I press tan 17, I get a number. If I multiply that by 6,732, I get the value of x, which is 2,058. And so our map actually had Mount Conness's height listed. And that was 12,590 feet. And we were standing at 10,550 feet. So the actual height was 2,040 feet. And we computed 2,058. So that's a difference of 18, pretty close. So the question you might be asking is, what happens if I don't have a map and compass? Well, you can always use the old-fashioned method, which is to look up at the sky. Now, people have been navigating around the globe for centuries by utilizing the heavens as their navigation method. Now, before I explain the concepts around the Earth's rotation and the revolution around the sun, I first need to explain space-time. Now, to help you understand space-time, I have an analogy. I used to work at a coffee shop in downtown Mountain View called Red Rock Cafe. And on Mondays, in the evenings, we would have something called open mic night, where a bunch of musicians would come in and they would perform. And it'd be very loud, and there'd be a lot of people, and it'd be noisy. But in the afternoons, it'd be very quiet. There'd be people on laptops and reading books and studying. And it was the same space, but it was a different time. And it was the combination of the space and the time that made open mic night what it was. And that's the key, is that as you're sitting there right now in space, watching this video, you are in space-time. Consider this. What is a day? Is a day 24 hours? Or is a day one 360-degree revolution of the Earth? Well, suppose you're on a plane and you're flying from LA across the globe, perhaps to India. Is a day still 24 hours? Or consider this. Let's say you're in San Francisco, which is right here. And if this is the sun and this is the Earth, this is the night side of the solar system because you're facing away from the sun. Now, if this right here is the starting point of your day or midnight, this is one 360-degree revolution of that day. But as the Earth revolves around the sun, for example, on this side of the solar system, that same 360-degree day now means that midnight is pointing at the sun. So you can see how the definition of a day really changes depending on the space-time. I have been talking a lot in my videos about the concept of a meridian line, and I've always said that north is your reference direction, and we're always trying to find a true meridian line on our maps. But now I want to show you how you can find a true meridian line in the field using no compass, but instead using the sun to figure out what is known as your apparent solar noon. Alright, so let me explain what I've done here. I have a paper towel holder here, and I've placed a sheet of paper down here, and what I'm doing is I'm marking with a Sharpie every 5 minutes where the shadow extends to. And what this is going to do is it's going to help me to figure out where my local apparent solar noon is. Now, if you don't have a paper towel holder and a piece of paper, you can use a trekking pole or draw in the sand or whatever you have available for you. This is going to help you determine your reference direction of north. All right, so here's a close-up of what I've been doing. And as you can see, I've been drawing these hash marks to the extent of the shadow and putting the times next to them as well in 5-minute increments. And as you can see, the shadow is getting shorter and shorter. And I'm going to continue doing this until I see that the shadow is starting to increase. At the lowest point, the shortest point of the shadow is going to be the direction of north. And that is true no matter where you are on the globe. All right, so what I have here is all the different points that I've drawn along with the times where I've taken each measurement. And so what I'm going to do is I'm going to basically measure to see which one is the shortest. And sliding my compass around here, it looks like the shortest is somewhere around here, 115. And, you know, looking at my compass, I can see that when I have the bezel oriented north, it is in fact pointing this direction. So that basically means this direction is north. So you might be able to find north during the daytime by figuring out your local apparent solar noon. But what if you're lost at night? Well, then you need to use the North Star, or Polaris. Now, the North Star is in the side of the constellation Ursa Minor. And if you imagine the night sky as a sphere surrounding the Earth, that is what is known as the celestial sphere. And Polaris is located at the north celestial pole. And because it's always in a fixed point, you can always use it to find north. Unlike the rest of the stars, however, which rotate, those require you, if you're going to use them to navigate, to know the time of day, the time of year, and the latitude. This caused a lot of problems for explorers in the past, and it was known as the longitude problem, because people did not have accurate timekeeping devices like they do today. So earlier in the video, I gave you a problem, and that was if you know two angles in a right triangle, what does the third angle have to be? And you might know the answer just because you're a math whiz, but I want to show you how you can figure it out logically. Because if you look at a right triangle, really what it is if you extend the triangle like this, and you make an imaginary secondary triangle, a right triangle is really just half of a rectangle. And a rectangle, as you may know, is comprised of nothing but right angles. And so then all the angles in a rectangle or a square are 90 degrees. And so these add up to 360. So if I take a triangle, I'm basically just taking half of that. So whatever angles I have in a right triangle, they have to add up to 180 degrees. So in this example, this angle has to be 73 degrees. Okay, so before I wrap up this video, I have a puzzle for you. This is the compass that you've seen me use in this video and in the previous one. And you'll notice that I tend to use a pencil in order to avoid affecting the magnetized needle. Because if I was to use a knife like this, that is going to affect the magnetized needle because the knife is made out of metal. And so you might conclude that metal affects the magnetized needle. However, aluminum is a metal, and this carabiner here is an aluminum zinc alloy. However, the carabiner does not affect the magnetized needle at all, even though aluminum is a metal. So the question is, why does the knife affect the magnetized needle, but the aluminum carabiner does not? Put your answer in the comments below. Alright, so that concludes my video for navigation, advanced concepts. If you have any questions, please feel free to drop them in the comments. And as always, thanks for watching and happy trails.